Good evening, everyone. Thank you. Good evening, everyone. Thank you so much. Let's start now. Please turn off your videos and audios as well. Right? Okay. Okay. Let's start. Did the school send you the board work that I sent them yesterday? Did you get anything from the school? Okay. Fine. All right. Okay. All right. You have not got it, right? Screen is not there to win. Don't worry, I have not started writing anything yet. I'm just talking to all of you. Okay, now we will start. Right? Uh, Fine, I will tell them to send it to you. Right? Okay. You are in 12. Okay, fine. So now I'm going to share the screen. So hopefully, let's talk like last year. What does that mean? Last year on Teachers' Day, we did not study. Is that what you are saying? No, but this time I think we should because okay, we have only covered one and a half of chapter, right? We still have a long way to go. Thank you, both of you. Thank you. Thank you so much, everyone. Okay, fine. Without waiting anymore, right? Let's start. So I hope everyone can see the screen now. Okay, two and a half, lesson 14 also covered. Okay, yeah, that's true. All right. Huh. Earlier we have studied some of the properties of conductors, right? This was the last one we studied, and that is that every point inside the body of conductor is at same potential, right? And that potential is same also at the surface. So based on that, we also wrote one sentence here that the surface of conductor is equipotential surface. Actually, I sent you these two sentences just in case you might not have been able to write it. But anyways, you didn't get it, so never mind. So now let's go to the next thing. Okay. Let's go to the next thing. So next property, how many have we done? This is five, right? Four, sorry. Now five. Now, frankly, I don't know how many are given in the book, right? But let's cover this one and then we'll check whether we have finished everything or not, or have we missed out on. All right. So this number five is about. We did five, really? Okay, fine. So this is number six. Sorry. Okay. So now this number six is about electrostatic shielding. All right. This number six is about electrostatic shielding. Right. So what is meaning of this? So this is where we are going to talk about hollow objects. Right. So here we are going to talk about hollow conductor. Right. Okay. So pay due attention. Right. So suppose this is some conductor, right? And it is hollow, right? Random shape, okay? It doesn't have to be sphere or anything, right? Random shape. So this is solid, right? This part is filled with metal or conductor, right? And this is empty part, all right? So this is a hollow conductor, right? Okay. So now, if suppose this conductor, right? If this conductor would have a charge, right? We are going to talk about several things. Suppose this conductor has a charge, right, like this. Let's say positive, okay. Negative also would not make any difference to the concept, right? So suppose it's like this. Then I hope you all remember that, at this place there is no charge, at this place, this place, this place, this place, this place. Over here, at all these places, there is no charge. Charge is only on this outer surface of this one, all right? Charge is only on the outer surface. Clear? Right? So what's the electric field here? It's zero, right? Okay. So now just like that, just like we did prove that electric field over there will be zero. Think about a similar idea here. If I'll take uh, Gaussian surfaces of any kind over here, right? Anywhere. I hope you realize that at each place we'll get flux equal to zero for any random shape, correct? Okay. And of course, right? Okay. So what this would mean is that at every point over here, right? At every point over here or here or here, all these points in this hollow region, the electric field will be zero. Is that clear? There are two ways to explain this. Of course, flux is zero. Uh, sorry, flux is zero for all cases, for all these things. Also, the potential will be uniform, right? I hope everyone remembers that. The potential is going to be uniform, right? So what happens is that all the charge over here on the surface, right? It's only going to create an electric field like this. Okay, electric field lines will not come inside, correct? Electric field lines will not come inside. So we can say that the interior of this, right? Okay, the hollow region of this conductor, right, has no electric field, all right, in this hollow region. Is that okay? Of course, there's no electric field here also, and there's no electric field here also. Did you understand? Okay, right? So far so good, right? We are going to change few things, okay, right? But before that, let me tell you what's the use of this kind of situation. See, what is meaning of shielding? Shielding means to protect. I'm sure you understand what I'm saying, right? Shielding means to protect, correct? So what we are saying is that this hollow region is actually shielded or protected, right? From what? From all the charge that is outside. Do you agree with that? I'm saying that this hollow region is protected or shielded, right? It is shielded from the electric field on the outside, right? That is, whatever is that electric field outside of it, or whatever is the charge outside of it, right? That has no effect on this part, right? Because here the electric field is zero. Did you understand this situation or this sentence actually? Okay, right. Now let's change situations a bit, right? Let's change all this. Suppose that, okay, we have same hollow conductor and everything, all right? Okay, right? Okay, and then let's, okay, fine. I'll just draw a new diagram. It will be better. This will become very untidy, all right? So the new situation I'm going to represent in a new diagram, right? So this is again that random shape hollow conductor, right? So this part is hollow, all right? It is empty. There's nothing of there, right? And let's say this may have charge, may not have charge, right? Doesn't matter, right? What we are going to talk about is very interesting, right? Suppose it does have, some charge, right? But it may not have a charge. I'm not even indicating, right? But let's say we put this conductor, let's say we put this conductor, means this body, this object, in external electric field. Let's say we put this object in external electric field. All right. Remember, this is in 3D. Don't forget that. 3D means it is a solid body, right? This is its body, right? And this is an empty region. Such empty regions are also called cavity. You understand what is meaning of cavity? Cavity means like a hole, all right, inside which you can sit. Okay, right? Just like bacteria would sit in the cavity in your teeth, right? Cavity means a region that is trapped from all sides. Okay, so this is empty region. This is like an empty region, but from all sides it is surrounded, right? Harsh, you will have to clarify what is not clear. Everyone else, is the meaning of cavity clear? See, this is not in 2D, right? This is in 3D. Okay, this is in 3D. So if if you say that in this cavity, if you put some object, let's say we put a torch which is giving light, then that light will not come out because it is trapped from all sides, right? એવું નહીં કે આમ ઉપરથી આવી જશે. That's nonsense. This is not in 2D, it is in 3D, right? So that is what is cavity. Can we assume a ball? Yes, if you want practical examples, I can give you examples of it. See, if you consider that there is a room, okay, with all walls, okay, with all walls, ceiling, and floor, right, and no doors or windows, right, okay, right, then the inside this room is a cavity, right? Inside the room is a cavity. Did you understand what is a cavity? I'm waiting for you all. Did you understand now what is a cavity? Right? Cavity is a space, right, in which you can get trapped and then you cannot go out. Right? That's called a cavity. See, this is not called a boundary. Boundary is in 2D. Suppose that is me, right? And I'm standing on the ground. And you draw a circle around me. Then this is called a boundary. This is not called cavity, right? I hope you understand what I'm saying, right? Because this is in 2D. 2D means two dimensions. On the other hand, cavity is in 3D. If someone is inside that room, think about it. Someone is inside this room, and there's no way to go out. No gaps or space in an object. Among gaps or space in an object are called cavity. Exactly. Yes, trapped from all sides. Correct. In 3D, okay, not in 2D. Fine. I think that's enough of explanation of cavity, right? Cavity is basically empty region surrounded from all sides. Okay, right? Empty region surrounded from everywhere, right? Okay. Now, so I'm saying that if we put this conductor which has a cavity, right, in an external electric field, right, that electric field may be of any kind, right, but see, let's say we have just put it, all right, you'll have to understand this very carefully because this is a process, right, regarding what happens with the electric field. So this is external electric field, right? I'm sure you understand what will happen is because of this external field in this metal, there are free electrons, and those free electrons, some of those will start coming over here. I hope you understood what I said, right? And some of the positive ions will settle on this surface, correct? I hope you still remember this idea, right? Do you remember this idea? Finally, what will happen is that these pink charges which have been separated or which have settled over here because you are applying this external field, right? So what has happened is these charges have settled here. So because of these pink charges, there will be an induced electric field like this. We have talked about this earlier also, all right? Okay. And finally, everything will settle such that when there is equilibrium, the induced electric field and external field, these are equal, right? Okay. So what I'm saying is that in equilibrium, that is when everything settles down. Again, we are talking about electrostatics. See, we are talking about electrostatics, right? So in equilibrium, what will we have? We will have that in this cavity region, right? For the cavity region, there will be two electric field. Which two? One is induced, right? And the other one is external. But both these fields will cancel each other, right? So ultimately in the cavity region or for the cavity region, what we have is net electric field will be zero because these two are in opposite direction. So and they will become equal in magnitude, so they will cancel each other. All right, okay, understood that? Yes or no? I'm waiting for you. It's just like what we did earlier, isn't it? Fine. I believe everyone has got it. Right? Now see, for a moment you might, even if you think that, even if you think that it is not in equilibrium, suppose you think that this is not in equilibrium, right? So what will happen is that in this region, right? What will happen is that in this region, there will be some net electric field. Suppose it's like this, net. Okay, net means total. So the same electric field will be there over here also, because things would not have settled yet. So in that case, what will happen is one of the electrons or a few more electrons will go over there, and now you'll have a few more plus and a few more minus. So then once again the induced electric field will increase and it will then cancel it. So finally, always when it is equilibrium in this region, the two fields will cancel each other, and here you will get equal to 0. Here also you'll get equal to 0. All right. So this is the important thing. It is as follows: even in presence of an external field, even in presence of an external field, the net electric field in a cavity, in a charge free cavity. Why am I writing charge free? I'll explain that very shortly. Even in presence of an electric external field, the net electric field in a charge free cavity made in a conductor is 0. Okay, now some of you have typed something. Will charges be induced near inner surface? Purvendra, I'll explain that very shortly, all right? Which I will also answer your question. Let me just explain this sentence first. Okay, so what have I written over here? I'm saying that suppose there is presence of external field, right? That is like this case, right? There is some external field. Now, even if there is an external field, the net electric field in a charge free cavity. What is meaning of charge free cavity? Okay, look at this cavity. Anywhere inside the cavity, over here or over here, or there is no charge, right? Okay, so in such a case, when the cavity does not have a charge, we call it charge free, right? Not sugar free. Okay, so in this charge free cavity, right, which is made in a conductor, right? Cavity એટલે hole કેમાં છે? wood માં છે? નહીં. The hole is in a conductor, right? So even if there is external field, the net electric field in the cavity, which is charge free, right, and the cavity is made in a conductor, this net electric field is 0, right? Is the sentence clear? I know it's a very long sentence. I'm waiting for you. Have you understood this completely? Tell me that first. You know, you can generalize this case. You can generalize this case and this case, right? Okay. And we can finally just write one sentence. Cavity in a conductor is shielded from all outside electric field or charges, right? I think this is a very simple way to say the same thing, right? Cavity in a conductor is shielded. Shielded means protected from all outside electric field or charges. That is any charge that is on the outside of conductor, for example like this one, has no effect on over here, right? Is that clear? So again, don't forget this sentence is only true for electrostatics, right? This sentence is only true for electrostatics, all right? So this sentence is called the idea of electrostatic shielding, right? This sentence is called the idea of electrostatic shielding. Shielding, that is, it is protecting, right? Okay. Now the two questions that were asked, right? One by Purvendra, the question was, will charges be induced in inner surface? And Vishwa, your question was, is electric field inside zero? Vishwa, I'll answer your question first. Yes, electric field inside is zero, right? Over here, this electric field is zero, right? Okay, fine. That will happen if the cavity is charge free, means it has no charge, right? Okay. And now Purvendra's question. What about inner surface? All right. What about inner surface? Okay. Let's see. Suppose this is a conductor, right? Okay. Suppose this is a conductor over here, right? So if you consider that this is all solid, right? Okay. Then, so if all of this is solid, right? And you see, there is no electric field here, right? There is no electric field here also, right? Okay. Yes, Sumit, will come to that point after this, all right? In fact, that's the next thing that we are going to discuss. So I'm saying that electric field over here is zero, right? Okay. But now if you will consider that, let's say, because of the external field, right, here on the left surface, some negative charges have settled, right? And on the right surface, some positive charges have settled, right? Now the question is it possible that there is some charge over here on this inner surface, right? So what is meaning of inner surface? This one, right? We are talking about that inner surface, right? Is it possible that there is some charge on inner surface, right? Purvendra, in this situation where there is only external field, right, where there is only external field, in such situations it is not possible, right? Okay, for such situations it is not possible. I'll tell you why. See, suppose at this inner surface there was a negative charge, right, which is not coming over there, right? Okay, suppose at the inner surface there was a negative charge which is not coming over there, right? Then this actually violates several things, right? In fact, it violates many of the properties that we have studied earlier, but I'll just use one to explain why this is wrong. It is that for this charge, if you consider this charge, right, every point on this metal is at same potential. I hope you remember, right? V is same everywhere, right? So for this charge over here, it is equally easy to go over there or here, right? Because every point is at same potential. So work done to go from one point to another will be zero, right? Because if potential is same, if V is same, this charge potential energy will also be same. I hope you understand what I'm saying, right? So in that case, it will not take any energy for this charge to go and meet the positive charge, right, and neutralize it, right? So what will happen is this charge will easily go and neutralize one of the positive charges. Now if that happens, this induced field will become weak, right, because one charge has been neutralized. So what happens is that once again some atom will have to throw out or remove its free electron, and once again we'll get one ion, and then that electron will not settle until it goes all the way there, right? Because it will be attracted by this external field, right? Okay, so again what I'm saying is, at any point, right, we have also studied that at any point in body of conductor, right, at any point in body of conductor there can be no charge, right? Okay, at any point in body of conductor there can be no extra charge or net charge, right? Okay, so if everything is in equilibrium, then these charges cannot be on in the body over here, right? Also, like I said, they cannot be on the surface. If it is over here at this surface, right, then it will flow, right, it will flow and go away, right? Is that clear? So that is why it's not possible that it is held on this point, right, on this surface, right? Okay, so keep that in mind, right? You can actually, if you consider, you can also use Gauss law to prove this or not. This can be proved wrong in so many ways. Let me also prove it using Gauss law. You might find it very direct. Suppose one positive charge decides to stay on this surface, right, inner surface, right? So in that case, if I will take a Gaussian surface like this which surrounds this charge, right, then there's going to be a problem, right? The problem is that although charge enclosed will be some q, but still the flux will be zero, because over here and over here and over here and everywhere the electric field is going to be zero, right? Okay, so that's why this is a contradiction. It is wrong. Okay, both of these things cannot happen together. So ultimately we can conclude that even if there is external field, right, all the charges will be still on the surface, right? They won't be over here, right? So that is what is necessary, right? Okay, now we go to the next case of the same thing, right? What if cavity has a charge inside it, right? See, this is the third case. So we are now not talking about charge-free cavity, but this is a cavity with a charge, right? Okay, to explain this, I'm going to take example of a sphere, right? Okay, because it's an easy shape, you will understand it better, right? So let's say this is a sphere, but this sphere is not solid. It is a hollow sphere. It is a hollow sphere, but with thick, or rather I should say it's a hollow sphere, but it is thick. What does that mean? It's like this. So you can't call it a shell. I hope you understand this is not a shell, right? Shell is actually supposed to be thin, right? That's the general meaning of a shell, right? But anyways, every real shell has some negligible thickness, but that's what we are saying, right? Let's say this has some thickness. So this is a cavity, right? This is a cavity here, right? And there may be external field or not, no problem. But I want all of you to consider that if you would place a positive charge in this cavity, let's say we put a positive charge at the center of this cavity, okay, right, and this is metal, what do you expect to happen? Can you tell me what do you expect to happen? There is no external field, no nothing right now, okay, and this metal is also neutral, okay. Can you tell me what do you expect to happen? It's fine if you are wrong. I've not even taught you yet about this. I want to know what's your intuition. I've not received any answers yet. Okay, I've received one answer. Hey, Chaitya, question બે વાર બોલો. I'm saying if you put this positive charge here, what do you expect to happen? What do you think will happen? Okay, right? Negative charges will surround it. Can't I have a negative charge codal? Charge will move to surface. Which charge will move? Kea, which charge will move? Electric field will radiate outwards. That's correct, Himani. But what happens to the metal conductor, right? What happens to that conductor? Okay, very good, Dhyan. All right, no effect. Nothing will happen, all right. Okay, right. Okay, fine. So let me answer this now. So what will happen is, listen to this carefully. Let's say you have just put it, all right? ત્યારે તો હજી તોફાન થતું હશે, right? There will be some changes going on. Yes, Himani, that's right. Okay, so many of you actually gave the right answer. Okay, it is that when you just put it, at that time the atoms of this metal, right, they will start losing their free electrons, right, and those free electrons will start getting settled on this inner surface, right? Is that okay? The free electrons will start getting settled on the inner surface. But because this was neutral, so total charge should be zero. Total charge on metal should be zero. Okay, I'm talking about metal body. Okay, right? So if negative charge will come here, right, that would also mean that the positive charge is repelled by the positive charge that you have put, and the positive charge will settle on the outer surface, right? So, so I can explain all of this by this sentence. The positive charge put at the center or put in the cavity, sorry, positive charge put in the cavity induces means attracts and brings, all right, induces negative charge on inner surface. Okay, induces negative charge on inner surface and positive charge on outer surface. Okay, right? So this is what has happened, right? Now can you tell me what is the electric field at this point P in electrostatics? All right, when everything is in equilibrium, what will be the value of EP? I wrote it, sorry, I'm so sorry. Naturally, I wrote it, and it is equal to 0, right? Okay. Fine. So this is going to be equal to 0 here, right? Okay. I'm going to ask you next question related to this. What will be the electric field direction at this point S, suppose? What is the direction of electric field at this point S? You have several options. No field, inwards, outwards. You have several options, people. At this point S. Okay. Yes, we are talking about electrostatics only, all right? We are talking about electrostatics. Okay, all right. If you are getting confused, don't worry. Tanay is giving me options. Come on, Tanay. All right, that's it. Would anyone else like to answer? We have had only 25 answers. Come on, people. હવે નામ બોલ લઈને કેવું પડશે. ऐश्वर्या, अमन, अर्षद, आर्य, महक, देवांशी, ध्यान, कनिष, केवल, Kunal. What are your answers? Harsh, Omdeep, Vandan, Ramyak, Sakshi, Sakshi, two times. What are your answers? Raj, Vivek, Tanas, come on. You told outwards. Okay, Amar. Right? આટલા બધા નામ બોલ્યો તો 5 જણે આન્સર આપ્યો હતો. ઓકે કે બાજુમાં બીજા મોબાઈલ ઉપર પિક્ચર નથી જોવા માંડ્યા ને? Well, let's see. I am not going to guess it. All right, we will prove it, right? And to prove it, we will use Gauss law. So let's say we draw a spherical Gaussian surface like this. Okay, for this Gaussian surface, what is charge enclosed? Is it 0 or not 0? Is it 0 or not 0? Okay, some of you have started saying not 0, right? If it is not 0, then is the charge enclosed positive or negative? So now I am giving you 3 possibilities: 0, positive, negative. Come on, 0, positive, negative. Which one? Okay, fine. Come on, people, this is clearly positive, isn't it? દેખાય તો છે ફિગરમાં, નથી દેખાતું? આ ગોસિયન સરફેસ, રાઈટ? એની અંદર કયો ચાર્જ છે? પોઝિટિવ ચાર્જ. એઝ સિમ્પલ એઝ ધેટ. બહારના શું કામ ગણવાના? એન્ક્લોઝડ મીન્સ વોટ? ઓકે, right? I hope everyone understood that it is positive, right? Negative will not attract single positive charge. What do you mean to say? Negative will not attract that single positive charge. It will attract, but it will still remain there. Okay, right? But it is in equilibrium state, so how can it be positive? Okay, fine. All right, so let me answer that question, right? It's that it's possible some of you are still thinking that here electric field and everything should be 0. But see, I'm not even asking you about electric field, right? I'm just saying that if we take this Gaussian surface, what is the charge trapped inside that Gaussian surface? All right, okay, I'm not asking you for anything else. All right, so I think it is quite clear that in that case charge enclosed should be some plus q, right? Because this positive charge is definitely inside it, right? And see, that's why I took a shell, right? How can one positive charge hold this many negative charge? won't it go to outer surface? No. I'm not saying this positive charge is holding everything or anything like that, right? Did I say that charge on surface is more? No, I'm not even saying that, right? Okay, I'm not saying that, right? I'm just saying that this positive charge here, if you put it over here, then it will induce a negative charge distributed on this whole surface. એટલે અહીંયા બધે થોડો થોડો નેગેટિવ આવી જશે. I'm not saying that this negative is more than this positive. I've never said such a sentence, right? I don't think I told you that, right? So what I'm saying is this positive charge will cause negative charge induced on the entire inner surface, right? But I'm not saying this negative charge is more than this positive charge. એવી તો કઈ વાત જ નથી થઈ, right? Anyways, if you are thinking would this charge not go on the side, no, that why? Simple. We took a sphere, right? We took a sphere, didn't we? And if you put the charge at the center and badi baju negative hoy, right, then what's going to happen? The electric field of this one, sorry, electric force of this one will attract it over there, but the force of this one will cancel it, right? Similarly, force of this one will pull it over there and the force of that one will pull it over there. Everything will be cancelled. એટલે move તો થાય જ નહીં, right? Is that clear? Okay or not okay? So this positive charge will remain where it is, and then like I said, if we are going to draw a Gaussian surface, it means sigma q enclosed is q. Now see, I hope all of you remember that I told you that if we take a Gaussian surface and we get sigma q enclosed positive, right? That means flux is also positive, correct? If flux is positive, that would definitely mean that the electric field is going outwards. Yes or no? યાદ છે ને, positive flux means outwards, right? Positive flux is outwards, negative flux is inwards. So okay, right? But won't outer surface positive charge, અરે હિમાની એમાં same જ થાય ને, right? Okay, because for this one, if this one will push it there, then the opposite one will push it like this. Once again, these forces are cancelled, right? I hope that does not confuse anyone. કારણ કે એમાં કઈ કન્ફ્યુઝ થવા જેવું છે જ નહીં, right? It's that simple. એટલે જ તો મેં સ્ફિયર લઈને સમજાવ્યું. પછી what? No, not clear, Tanaz? Suppose there is a positive charge here and here, right? Wouldn't that positive charge apply force on this positive in this direction? This one will apply force in this direction, and the other one will apply force in opposite direction. So it will get cancelled anyway, right? હજી આનાથી એ જોરદાર એક્સપ્લેનેશન છે, પણ અત્યારે આ સમજી લો, પછી થોડાક ટાઈમ પછી ઓલું સમજાવ, right? So all the forces are going to get cancelled and there will be no force on this charge, so this will not move anywhere, right? Again, like I said, charge enclosed by the Gaussian surface is positive. If charge enclosed is positive, flux is positive, it means the electric field is outward. So those who said outwards, your answer is right. Okay, all this discussion actually started from that question, right? આવું થાય. This is the true diagram of electric field. It will look like this. Okay, and there is positive charge here on this side of surface, right? Okay, from there the electric field lines will once again go out like this. You know, it's very interesting if we draw a field line diagram. Just give me a moment. So this is conductor. Let's say it's a sphere, right? But hollow sphere, like this. So અહીંયા પોઝિટિવ ચાર્જ મૂકો ને તો શું થાય ખબર છે? ફિલ્ડ લાઇન્સ અહીંથી આમ જશે, right? Okay, there the field lines will end, and then because positive charge is induced over here, yaad chhe ne? Like I said, positive charge is induced, green charge is induced, all right? The green charge is induced and red is what we had put. So then field lines will start from here once again. Did you understand this diagram? Why are there no field lines here? Why are there no field lines over there? Like cavity means empty surface, એવું નહોતું કીધું. No, Krupa, your answer is wrong. Chaitya, cavity means hollow region. Okay, that is called cavity. And the previous property was about charge-free cavity. This is not a charge-free cavity. Read that sentence again. That was for a charge-free cavity. Because it ended on negative, answer સારો ન કહેવાય. It's correct, but it's not a very, not a proper one according to physics. Neutral is wrong. Krupa, neutral is wrong. No, Kya, wrong answer. Yes, Omdeep, well done. Correct answer, Devanshi. Yes, Sakshi, correct answer. Yes, Darshi, right answer, right answer. No, Arshad, wrong answer. Wrong answer, Khushi. No, Pia, that's not the right answer. Well, people, this is the body of conductor, yes or no? And inside the body of conductor, you have electric field 0 in the body of this conductor. Everywhere the electric field is 0. If electric field is 0, obviously there are no field lines. Okay. Yeah, you could say V is constant, Arshad, but I think this is a simple reason that I said, right? Is this reason clear? Okay. Actually, that makes me draw one diagram, right? Okay. So suppose that this is a neutral hollow sphere, all right? Understood? This is a neutral hollow sphere, right? And if we put this in external field, right? If we put this in external field, okay, right? Or no, just a minute, sorry, let me change it, right? Let's say here we put a charge plus Q, all right? Here we put a charge plus Q, okay? Then I'm going to draw a diagram here, okay, and you have to tell me what is wrong with that diagram, all right? Yes, Chaitya, you understood that right. Okay, so if we put a positive charge here, then you have to tell me what's wrong with this diagram, all right? Tell me what's wrong. There are more than one thing wrong. Okay, there are multiple things that are wrong here in this diagram. Remember again that this part is solid. All right, this part is solid. Cavity અહીંયા છે. What is wrong with this diagram? ઇલેક્ટ્રિક ફિલ્ડ વચ્ચેથી કપાઈ જાય એ ખોટું, તો કપાવું ન જોઈએ, સીધું સીધું જોવું જોઈએ. Field line will not go inside sphere. There will be no field line in cavity. Mega field line is not going in the body anyway, right? Holosphere is, what are you saying, Omdeep? Holosphere is always 3D. Sphere cannot be 2D. Of course, I cannot draw a sphere here. It's impossible to draw a holosphere, right? That can't be passed. અને pronouns ને use કરવાના. What is that? Bullet? Electric field inside the cavity. Okay. There can't be field lines inside cavity. All right. In cavity, E should be 0. Okay. Right. There should be no field line in cavity. Okay. Huh. Net electric field inside should be 0. Inside cavity, E is 0. Okay. Field can pass through cavity. Yeah. Field can pass through cavity. Okay, Avinash, you are right. Well done. Okay, Shivangi, that's right. It will create, actually you should write induce, Darshi. It will induce negative charge on outside of sphere, on the left side. Okay, and on right side it will be positive. That's right, Purvendra. Yes, Pia, that's correct answer. Tanay, field line, barabar. Yes, Shivangi, well done. Create no induce, Darshi. There can't be electric field in the cavity. Yes, correct, Vivek. That's right. Which one field lines are not passing through solid area. That's why I've done dotted, right? Okay. No, there is no electric field in solid area, solid region. Harshad, dotted, I've drawn dotted lines. It means there are no field lines over there, right? It khali main straight indicate karu. Okay. All right. So, yes, now that's right. Induced electric charge. So many of you gave the correct answer, right? I'm actually very happy about that. I will the part later on. Okay, we'll just cover this and we will stop. The mistake here is one. Electric field line inside the cavity should not be there, right? Because this is a charge-free cavity. Can I say charge cavity in under? No. So that's why this is charge-free cavity. If it's charge-free cavity, then electric field inside cavity should be 0, right? Okay. So that's one thing this is wrong. Our line khoti hai. Okay, we should remove it. The second thing that is wrong, but only some of you identified it, is that electric field is perpendicular to surface. भूल गया ने? Electric field is perpendicular to surface. So that's the other thing wrong. એટલે સાચો diagram છે ને આવો કંઈક આવે. Suppose this is the suppose this is the sphere, right? And this is the cavity inside it. Then the electric field lines will come out from this charge but then they will bend. આમ થશે. I hope that makes sense to you. Why? Because there will be negative charge induced on this surface. અહીંયા minus આવશે, અહીંયા minus આવશે, અહીંયા minus આવશે, અહીંયા minus આવશે, અહીંયા minus આવશે. Right? Okay, and of course here there is field 0, here also there is field 0. બસ અહીંયા લાઇન્સ પૂરી. પછી છે ને બીજી લાઇન્સ અહીંયા જે પ્લસ હોય ને ત્યાંથી નીકળશે. આમ from here one line will go straight, this one, right? બાકીનું પછી આમ થશે. I hope you have understood, but every point this angle should be 90, right? I hope you understand what I'm saying. At every point this angle should be 90 because electric field is perpendicular to the surface. So this is going to be the diagram. All right, so with that we are going to stop. Okay, tomorrow sorry, we'll continue on Monday. All right, goodbye.